Voy a empezar ya. Okay, so good morning. So just one announcement. So we didn't cover backpropagation yesterday, but I think Estelle is going to post the notes somewhere in Slack, so you can have a look. So they're very nicely written and clear. Okay, so you can have a look at what that is, and which is basically what we said is a nice way of like writing this chain rule to train or to compute the gradients of those cost functions when you have this like multi-layer perceptron or multi-layer feed-forward neural net. Okay, and for today we're gonna describe a little bit of an introduction to unsupervised learning. So it's again unsupervised learning, and it's going to be pretty informal, almost just a couple of equations, but I hope you find it useful anyways. So as I was saying yesterday, so you can have many different types of situations or settings when you're doing unsupervised learning. Okay, so and one of them we mentioned, like one of the ones we mentioned was this idea of finding low-dimensional representations of your data sets, right? Like, so low-dimensional representation. Of your data sets, right? Like, so, and what I meant by that is, for instance, if you take this handwritten digits data set, that you can then project it somehow into this lower dimensional space, let's say in 2 dimensions, and then you'll see some like meaningful representation of this data, right? Like, and as we mentioned, if we did this kind of like low dimensional representation for this data set with 10 different categories, then you will see 10 different blobs in this 2D representation, and that such that what you see is kind of like a meaningful, right? Like, so you can use this low dimensional representations as a way of understanding structure in your data set in a way that is easy to like for our brains to visualize, right? Because for instance, this handwritten digit, they're very easy to see and to recognize, but for the computer, as I said, it's just a string of bits. Okay. So we want to see like low-dimensional representations, and for this type of data set, it's very clear what it means and what they are, but you may encounter cases where you have data sets that you can't understand so easily, so it's always good to try to understand what's going on in a low-dimensional representation. And I'm going to describe one example that is called principal component analysis. Okay, so a particular example of a low-dimensional representation is called principal component analysis. That's PCA. Okay, so so this is the setting. Like, so what is the data set? So experience or data set is this one. So it's a set of, say, images or spin configurations like the ones we've been using and demonstrating in the tutorials, sound files, sequences of text, you name it. But in principle, there's no labels, right? Like, so even though you can add the labels to your vectors and so on, in principle, you don't need labels, right? Like, so in principle, no labels, meaning you don't need this supervision, right? Like, as you saw in the tutorial, we had this 3 or 4 branches, and we had the corresponding labels. They were the labels corresponding to which branch this data set came from, or this particular point came from. Okay, so in this case, we don't need to, right? We don't need labels. So, and this PCA is basically a way to extract important information from this data set. Okay, so what is the data set in PCA? It's the usual, right? There's design matrix that I described, which is just a collection of vectors, right? Like x1, x2, all the way through xm. Okay. where xi is in Rn, such that this matrix, this design matrix is what? Oops, sorry, is n. Sorry, let's make it bigger. M by n. Okay. Okay, so that's my data set, and how are we going to find this PCA representation, or this? How are we going to extract this important information, or this structure in the data, right? Like, so first we're going to shift these vectors I to minus the mean vector over the entire data set. Okay, so it's kind of like the mean, the average of these vectors. Okay, so that's the first thing. So from now on, when I write x, I mean xi minus the original ones minus the mean. Okay, so that's the thing. The first thing. So what we do, or what we want to do, or the idea with PCA is to find a new basis to represent this data set in terms of the principal components, and I'm going to try to describe what they are. And these principal components are such that the data set in this new basis looks uncorrelated. Okay, and I'm going to explain what I mean by that in a minute. And the idea is that we want to find this new basis where the data set looks uncorrelated, because when there are correlations or perfect correlations between data set, it is kind of like equivalent. I mean, let me just give you an extreme example. Suppose you have two variables, like it's x2 and x1. X1, and that there's a perfect correlation between x1 and x2. Okay, let's say they're related by linear relation. Okay, it means that if you know x1, you can perfectly know the value of x2. Okay, and so these variables are perfectly correlated. Okay, and so what we're trying to do is to find this low D representation, meaning we want to get rid of these relations. Okay, these correlations in the data. So what we want to do is to find a new basis set to represent my vectors x in a basis where we want to get rid of these correlations. Okay, so that's the spirit of principal component analysis. Okay, and so let me tell you what I mean by correlation. Okay, so suppose you have two vectors a1, a2 through an, and vector b, b1 through bn. So we're going to quantify correlation through the so-called covariance matrix, okay, or the covariance of these variables. And it looks like this, right? Sigma AB is this object. This is 1 over n minus 1, where n is the dimension of the vector, and then you have A dot B transpose. Okay, so this measures the correlation, okay, between these data points, and we can generalize this idea, like which I wrote for two vectors, for the entire data set that we have. Oops. Should be careful. Okay, so so what is the covariance matrix for this data set? That's the question. So it's this object. I'm going to call it SX, meaning covariance matrix of my data set X. It is this thing. Okay, so it's 1 over n minus 1 X times X transpose, where this is my design matrix. Okay, so let me write it here. All right, so that's the basic idea. So that we know we have this data set, we have a big bunch of m vectors. We can construct this covariance matrix, and this matrix informs us about the correlations in the data. Okay, and we want to get rid of those correlations. or I find a new basis set where my data looks uncorrelated. Okay. So what is this transformation? So it's going to be a linear transformation. Yeah.
Shouldn't that n be an m because there are m vectors?
No. So the question is, should this n be an m? And the answer is no. So this is the definition.
Oh.
Okay. Okay. So let me tell you first, before going into how we do this, like 2 or 3 properties about this matrix. Okay. So first, the off-diagonal elements. This quantify correlations between the components in the vector. Okay, so the correlations in the data between the different components in the vectors x. Okay, and the diagonal one, it quantifies what? It quantifies the variance of each of the components. Okay. So now let's just get to the point of PCA, or how to achieve this, like the goal of PCA. So PCA. So there are, like, at least I know about 5 ways of approaching this problem. I'm going to give you one based on linear algebra, okay? Just, I think, the simplest, or one that brings the least amount of ideas. And then I'm going to explain 2 ways of thinking about PCA that are not this initial version that I'm going to describe in detail, okay? So the idea is the following. We want to find, find an orthonormal matrix P such that it rotates these vectors x into vectors y, such that P, that there's a linear relation between the two, okay? So this P is, as you probably guessed, they're going to be called the principal components, okay? And this is the relation, if you want. So what we want to achieve is to find this new representations for x, where the correlations in this new data set, or the new design matrix, are uncorrelated, okay? So that's the idea. So how do we find that? So let's just construct the covariance matrix in this new space, or new representation, right? So it's 1 over n minus 1 of y transpose, okay? And then we can plug this in here, all right? So let's do it. So it's 1 over n minus 1 of px times px transpose, which is basically this thing. So it's px x transpose p transpose divided by n minus 1, okay? And this is what? The original correlation covariance matrix, okay? So it's P S X P transpose, okay? So, and this is SY, okay? So what this is telling us is this just basically a rotation or a transformation on your original covariance matrix, such that what? So that the new covariance matrix is what? It looks uncorrelated. And what quantifies those correlations? like the off-diagonal elements, right? And so it means that you want to transform this covariance matrix into a diagonal matrix, okay? Yeah.
I think that the covariance matrix of Sx is with respect to is over m. It's not n because we start with m elements. So as you said in the first example, AB
Okay.
has n elements, and so far we should have m. We have a matrix m.
Okay.
So there are n.
Okay, so I should replace n with m. So maybe I should simply
Only change
flip this. Oh no, this is fine. So maybe I just should add m here. Okay, sorry about that. I may have made a mistake. Okay. Sorry. Yeah, I'm sorry about someone else asked earlier.
But I think it's just n, not just n. That's one.
Sorry?
I think that is just n.
That's what I think it's fine. I think so. So when you have variance, usually you have 1 over m minus 1, right? Okay. Anyway.
It doesn't matter. Whatever constant you pick, you'll get the same p.
Yeah, that's right.
Diagonalizing the symmetric.
That's right. That's right. Okay. But thanks for pointing out, like, for this, and thanks to like the first person who pointed out. Then I said it was wrong. Sorry. Okay. So let me go ahead. So what? So yeah. So as I was saying, like, what this is telling us is that we need to take this original covariance matrix and find the diagonal version of it through this transformation P, right? And how do we do this? We diagonalize the matrix, right? Like S, or let me see. Yeah. So yeah. So if so if we x times x transpose, and we write it this way. So P transpose D P, then I think we achieve what we want, right? Like, so we can write x as y is P times P transpose D, so 1 over n minus 1 D P transpose. Okay, and since this matrix is symmetric, then this corresponds, this P times P transpose is the identity. Okay, and so we get our, so 1 over, sorry, I'm going back to my mistake, times this matrix D. Okay, so
the leftmost term should be P S Y P. Oh no, it says Y. Sorry, that's fine.
Okay, and so that with this, like, we achieved what we wanted, right? Which was to find a new basis set where the data set looks uncorrelated. Okay, and what are the diagonals of this D? Sorry, of this matrix?
The values of the x times x transpose.
That's right, but they look like what? Like the variance in this new basis, right? But then the off-diagonal elements are 0, right? Because when you diagonalize, you find the matrix that is diagonal with the eigenvalues being the variance of the data in this new basis. Okay, so let me give you a quick cartoon. let's say this is, we're in 2D, x1, x2, and let me just like plot my data set, okay? So let's say that my data set looks like this, right? So if you do PCA on this two-dimensional data set, you would find something like this. There's some different axes, y1 and y2, such that the data looks the most uncorrelated, right? So you can see I try to draw a data set that looks like, in which what you see is that there's some kind of like correlation between x and x1 and x2, but now we rotate this frame of reference to axis y1 and y2, such that the data will look more uncorrelated. And so this you can think about it as the noise. So this is quote unquote, okay, and this is the quote unquote signal, okay. And this kind of like distance here, the signal corresponds to an estimation of the variance of the data along these dimensions. So they correspond to the eigenvalue, the largest eigenvalue of this matrix, okay. Whereas the second one, the noise, is this one here is the second eigenvalue. So the second entry in this matrix, okay. That's the second variance, the noisy variance, like the noise, what we call the noise. So the transformation is linear, as this one here, which means that you can only hope to separate or like use this whenever a linear transformation is enough, right? Like so, works for. So I wrote this here. So it can only deal with data that is linearly understandable, okay, or linearly separable by this transformation P, okay. So that's the idea of PCA in half an hour.
You're assuming that your observations will mean zero.
I initially mentioned that I was going to shift x into x minus the mean vector, right? So all this, you're right, assumes that this x and x1 and x2 have mean zero, okay? Which I wrote at the beginning, okay? Okay, so let me give you a quick, yeah.
And one also has to perform feature scanning before doing PCA, or it's not that, I don't know. Is it necessary to perform feature scanning before performing PCA?
Okay, so the question is it necessary to perform feature scaling before doing PCA? So formally not, but then people in practice do it, okay? The geometry of PCA, let me tell you a little bit about this. It's a different point of view, so this part is even more informal, so it's just almost words. But let me tell you anyways. So geometry of PCA. So ideally, so when you do PCA, you want say you start from a high dimensional space. In this case, it's 2 dimensions, right? And then you want to go into a new basis set where the data looks more like simpler, right? So in here, if we think this as the noise, then we can ignore it, right? So we go to a lower dimensional space, which is this x1. The dimensions or the directions in which the variance is the highest, okay? As given by the first eigenvalue of the this diagonal matrix D, okay? So this is gonna be my like subspace where my data looks more understandable, okay? So it's this dimension, okay? So that corresponds to just projecting the data into a subspace that is lower dimensional, okay? And so I'm going to explain, try to argue this like geometry. So you have a space, like say 3D, where my data set lives. So you have, say, 1 point x here. Okay? So this is, again, unshifted, so before subtracting the mean. Okay? So I'm back to, say, x. Subtracting mean mu. So we have this point here, and then we have a subspace that looks like this. Okay, and let's say that the mean belongs to the subspace. Okay, so it's gonna be my mu, my vector mu, and this is my point x. Okay, and my subspace is gonna be S, is this plane here. Okay, so the idea is, so the observations is P, this P that we found, or P transpose, forms an orthonormal basis for the subspace S. Okay, so let me write this down here. So for S. So this is true when you truncate, okay? So when you get rid of this first, so you get this least important direction, okay? So P still forms a basis for the subspace. So I'm gonna write, like, say, P1 transpose and P2 transpose. So it's an orthonormal basis in this new space that we're gonna call like the simplified space, or the lower dimensional space where my data looks all right. Okay. So the projection of X onto this subspace is, say, the closest vector X. I'm gonna call it, like tilde. That's the projection on the plane, the closest vector to X in this subspace. Okay, so this vector here that connects, is going to be P transpose Y. Okay, and which means basically that X, my reconstruction, or like my approximation of X, so my approximation X tilde to my original vector in the higher dimensional space X is this one here. So it's P transpose Y plus the mean. Okay, so it's this vector here. It's an approximation to X in this lower dimensional space. That's the geometry of the whole thing. So P forms basis, and then the projection of X onto S is and it's the closest you can find. Okay, if you do PCA. There's one more thing here that I wanted to point out. So Y is called the representation or code. Okay, so that's the geometrical interpretation of this PCA. All right, so you find a space, a subspace S, where the data looks more reasonable, such that this projection is the best you can find. You can start from this and derive the whole thing without introducing these linear algebra ideas. Okay, it's only as a minimization problem in this setting. So that's the second way of rephrasing PCA. And let me give you the last one, last representation before going into a new topic. So it's that PCA can be understood as a so-called linear autoencoder. Okay, let me show you quickly this idea. So linear autoencoder. So what is an autoencoder? It's basically a map from high dimensional space to a lower one. Okay, which you already see where I'm going, right? So, and autoencoders are usually okay. You start from, say, original space where your vectors live. Okay, you apply some transformation, you get to a lower dimensional space, and then you try to go back to this X space. Since you impose a type of bottleneck where you reduce the amount of information, then this X is not going to be perfectly reconstructing your original input X. Okay, so X tilde is an approximation or a reconstruction of your original data X. If you put a lower dimensional code, people call this in auto. So this is why they call it autoencoder, because you start from a X, you encode it, you put it in a code, and then you decode it back into the original space as an approximate reconstruction of the original data. Okay. So if you assume that the transformation between X and the code is a linear transformation, let's call it W1. So it's represented by a matrix plus some shift, in this case the mean. Okay, and you have a second matrix here as a decoder, and everything is linear. Then you train this thing such that the input tries to find the best that this X tilde is the best reconstruction of your original data set. Then you're doing exactly PCA. Okay, and basically what you find is this. So W1 turns out to be P, the principal components, and W2 is P dagger, P transpose. Okay, so that's a third kind of like interpretation out of which you can start the whole thing and get to the same point. All right. So let me go ahead with what I wanted to tell you, which is the next idea in unsupervised learning, which is going to be very useful for the next lecture by Giacomo. Okay, so it's the idea of the maximum likelihood estimation. So let me get rid of this. Let's start here. Okay, so maximum likelihood estimation. So what is it? So consider again a data set, as usual, of examples X, right? Like big X. So x1, x2 through xm. So the same thing as before, and we assume that this data set comes distributed according to some unknown distribution that I'm gonna call Q data of X. Okay, so that's my setting. And we would like, so we don't know what this distribution is, because actually Roger posed this question in his first lecture. Like, suppose X, this features are images of cats, right? And then you take 1 million pictures of cats on the internet. Can you assign a distribution over the set of images? That's what I'm assuming here, right? That there's such a distribution. Even though philosophically Roger was arguing, does it even make sense? But we will assume it does. So it's this thing here. And so the idea of maximum likelihood estimation is that we're going to propose a model distribution that approximates this, this distribution that we imagine is out there in the universe. Okay? So we're going to propose a model, P model, which is a function of x parameterized by some set of parameters. So you can start thinking, what is this model, right? Like, so your favorite neural net, or anything you want, like any function that correctly parameterizes a probability distribution. Okay, so it can be your neural net or a simple Gaussian distribution with parameters mu and sigma and so on. Okay, so that's going to be my there's a model distribution, and the purpose of maximum likelihood estimation is we want to estimate theta. Okay, what is the best theta compatible with this data set that we have? Okay, so you take all the images in the internet from a cat, you construct a model that's reasonable, and then you try to find the parameters theta such that if you get samples out of this model, what you see is a cat, right? That's the idea. In our setting is a little bit different, right? Like, so you take a quantum system, for instance, and you measure it, you get snapshots like spin configurations and so on, and then you want to say, what is my the original distribution? We want to estimate what the original distribution, the original quantum state is. Out of these measurements, can you get this, and then can you use it to measure something else, like a sample, and get more statistics out of this model of the quantum state of, say, a device, right? Or your laser, and so on, or your quantum computer. Okay, so that's the idea with this. And the problem is relatively simple, right? Like, so you have to assume that this data is distributed from this, so according to this distribution, and it's independently sampled. And with, like, if you do that, then you can say, okay, what is the probability of seeing this data set if we was sampled out of this model P? Okay, so what is this probability? So what is the probability of the data set under this model if they're drawn independently? So it's basically, what is the probability of the data set is a product over 1 all the way through m of P model of what? Of the points that I saw, right? Sorry. Okay. And the maximum likelihood principle is the following. It's just this idea that if we see data in real life, it means that this data has high probability. Okay? Why? Because we observe it, right? Like, if it wasn't likely, you wouldn't see it when you go and measure your quantum system, or when you take a picture, it's not random noise, right? You see a cat. So it means it's likely that it looks like what you see in the data. So that's the idea. So what we want to do is, okay, this is the probability of observing this data. So what we want to do is we want to maximize this probability here with respect to the parameters that you have. Okay? So the maximum likelihood estimation of your parameters theta is this arg max of theta, of this probability. Okay? And this argmax function is basically find the theta that such that this probability here is maximum, and that's your estimation for the theta. Okay, so for numerical reasons, so probability is always a number less than 1, less or equal than 1. So if you multiply a big bunch of them, like say where m is large, when you have a large data set, so this number is going to be really small, exponentially small. Okay, so we usually deal with log of this probability. Okay, because log of this very tiny numbers is a reasonable number. Okay, so we rephrase usually this problem as, and also because logarithm is a monotonous function, right? It's a growing function. So usually we transform this into arg max of the log of this, right? Of p. All right, which is, if you want, is this. Let me see. So. Of log okay, I don't know if this is more or less clear. So what I do first here is you bring this log, you transform it into a sum. Okay, so log of the product is a sum. Okay, and then so basically, let me do it right. Arg max of sum over I. Sorry, yeah, xi. This xi comes distributed according to the original distribution q. Okay, and then I have log of p model of xi and theta, and this is approximately equal to expectation value, because this averages over x distributed according to q of the log of the model. Okay, so I write this sum here as expectation value over x distributed according to your data. Okay, and this is called this is called the so-called KL divergence between the P data, so the Q data, and the P model, which is kind of like a idea of like distance for probability distributions. Okay, so it's not a rigorous distance. It doesn't satisfy Schwarz inequality or any of those things, but it is always greater or equal than 0, and 0 when the distribution Q coincides with the model. Okay, so it can be used as a divergence, so that's the right word. So it's not a distance, but we can think of this as a quote-unquote distance in probability space. All right, and that's what I think I'm gonna stop here. So the idea is we use this KL divergence and this principle of maximum likelihood when we have data set X and we want to like produce an approximation or a reconstruction of the probability distribution parameterized by a model with parameters theta. Okay, so it's if you want, this is a way of inferring probability distributions given a model.
Let me see if I understand. You have like a lot of data, unlabeled data, for example, pictures of cats, and you try to approximate a probability distribution associated with that data, and then with KL divergence, you can measure the difference between that estimation of the probability distribution and the one of your model. So you can use that as a cost function to adjust the parameters of the model in order to approximate the distribution of the data.
Perfect. So the question was, think I have minus here. So the question was, is it the point of this whole thing that I have data set X that comes distributed according to some imaginary distribution that we found on the internet or anywhere, and the idea that, is it the idea that we want to use this whole idea to find a model that approximates this distribution, and we optimize this parameters theta such that this P model approximates Q, and to do that we use this KL divergence as our cost function, and the answer is yes. So I'm supposed to repeat the questions for the camera. So I think I'll leave it there, and another question. Sorry. Was there another question? No. Okay.
More questions or comments?
That's not too strong assumptions in order to, when new data is coming in our model, in order to predict what happens. It's not too strong assume that the whole training data is distributed by Q.
Yeah, I think it is a very strong assumption, and like the world is dynamic and can change this evolution, and so it becomes pretty philosophical, right? Like, and that's I wrote it explicitly. It's an assumption, right? So you call it strong. I agree. I didn't repeat the question, but yeah.
Por Slack.
La pregunta.
Ok, pero entonces, ¿cómo quieren? Pero sí, simplemente te paso a Juan. Y tú preguntas, ¿y él repite la pregunta? ¿Sí?
Ok.
No, o sea, no, yo te lo paso, él le repite la pregunta.
Ah, ok.
Ah, ahorita. Ok, bueno.
I think I made a mistake right there.
For the minus?
For some minus. This is not the KL, I think.
It's not.
Yeah, it's not.
It's fine. I'll redefine it anyway.
Yeah, okay.
Hello? Hello? Yes.
Hello?
Yeah? Hi?
Hello?
Yes? Can you hear me?
Hello?
Yeah?
Okay, I understood. So in principal component analysis, what do you mean by uncorrelated? Is that, I think I got it right. And so what do we mean by uncorrelated? So we quantify the correlations in the data?
In principal component analysis, what do you mean by uncorrelated?
No, I got it.
Because it is a delay.
Oh, delay, yeah.
It's
So now they're going to watch this again.
Solve the picture.
You should start.
Let's go ahead and answer.
Okay, so in principal components analysis, what do you mean by uncorrelated? I didn't have to repeat that, but just to mess with them. So we introduced this notion of correlation as computed by the this covariance matrix, right? Like, so it's basically what you end up seeing is something that looks like this, right? Like xi, xj, where these are components in the vector, right? Like, and so what you end up with is on an average of over this different components i and j. So that's kind of like the idea with this covariance matrix. So an expectation value, if you want, over your data set of this quantity as a correlation function, right? Like, how is this variable xi correlated to xj? Okay, and if this is positive or negative, then you say, if it is positive, then this means this two components are correlated. If they're negative, then you say they're anti-correlated, right? And what we did with the whole procedure of principal component analysis was to go into a new basis where all these possible correlations between yi and yj are what? Are 0. Okay, so that's what I mean by like finding a new basis where the data looks uncorrelated. I can discuss more like during the break with the student.
I play. So wait, you call me on WhatsApp and then recall or record? Send me another message, okay. Okay, good, send me another message. Okay. Parece que tiene más preguntas.
Okay.
Que me va a llamar un mensaje de audio.
Monica, the question was, if I get it right, that in PCA, how do you decide when to cut off the number of relevant components?
So
wait, maybe you send an audio message here, because.
I see. So let me think. So how do you decide where to cut off the number of components? So I think this is something that you do. You just take a look at the biggest ones, and then you basically decide where to cut. But you have to try several ones and see where it makes sense. So let me try to.
No, you send it to me?
Oh, I didn't send it to him.
Oh.
Okay, so let me try. Okay, so I think this is something you do in practice. You have to try several ones. So basically, you start with so these eigenvalues come in an order. So you start with the first, and then you do a plot and see if it makes sense. Then the second, then the third, and so on until everything makes sense. So, but usually the spectrum looks very clear, right? Like you'll see during the tutorial that there's some components that are very large and some other ones that are very small, and it's pretty clear. So this is something that you do in practice. So there's no rigorous or like predefined way of doing it.
Did you send it?
I did, I think. Don't send the answer. Maybe they're hearing it. I don't know.
You can see it.
YouTube, right?
Yeah. So they heard my first answer, now they got the second one. It should be clear. I think you should.
Yeah.
Okay. So if there are no more questions, which we can answer simply, then we thank Juan.
Thank you.
Fine? Yeah. Okay.
Should I introduce you or?
No, I guess it's fine. Yeah. Okay, so I'm Giacomo, and yeah, I'll be talking exactly of what the question was, how we can learn like an unknown distribution from data, and that's what unsupervised learning is. And so we're going to be looking at generative modeling, and in particular to the restricted Boltzmann machine. And so let me just say a few words about this, just to give some context. And because the restricted Boltzmann machine, or like RBM, played like a very crucial role in machine learning. And it was, so it's not being used routinely, like nowadays in machine learning application in industry. There are like more powerful algorithms, but it was a key piece in the like deep learning revolution of like 10 years ago. And in particular, it was used to pre-train layers of deep neural networks. So there was like some long-standing problem, like image classification, that was that were solved. There were some like breakthroughs in like 2012, and RBM were used to build like internal representation of this distribution. So if you imagine like doing image classification of like cats and dogs, you would do it with supervised learning, the one that you've seen yesterday. And RBM were used to pre-train every layer of this deep network to build like a representation of the distribution. So in some sense, you would teach the network like that, you know, there is this animal with like a long neck and is yellow, and this other animal that has whiskers and etc. And then by the end, you would say, okay, this is a giraffe, and this is a cat, and this was the supervised learning part. And this procedure, it was very powerful and led to these breakthroughs. And even before, RBM it was one of the main contributions in the 80s that led to the resurgence of this field. And so one was backpropagation, and the other was the invention of the RBM. This is like early 1982 or so. And it's interesting that RBM, in fact, are like a special type of neural networks, and they were physics inspired. So there were some early work by two physicists, like William Little and John Hopfield, and condensed matter physicists. And so it was going to be clear when I go through this RBM that this is nothing more than an Ising model, essentially the same that you see in the first day. And so this type of network was then adopted recently, like in the last 2 or 3 years, by the physics community. And since it's essentially an Ising model, it's straightforward to use this type of network to be a representation of physical states. So it's very natural to use it, for example, to like represent like a Boltzmann distribution of some thermal system, and that's what you're going to do tomorrow in the tutorial. And then it's also fairly straightforward to use this network to be a representation of wave functions, and same with density operators, say for like open quantum systems. And so what this is essentially, it shares many similarities with the feed-forward neural network that you've seen yesterday. So he has a collection of neurons, and these neurons represent variables. And you have edges with weights, and these represent conditional dependence between your variables. But one important difference is that these neurons are stochastic, so that's why it's essentially equivalent to an Ising model. And so from this representational point of view, you can use it to represent state and quantum state, and then you can use all this unsupervised learning machinery to essentially extract feature from data. And so one example that I'm going to go through tomorrow, it's quantum state reconstruction. So that's what Juan was alluding to. So you have like some data generated by some quantum system. This could be like a generic quantum hardware. And so when I say hardware, I mean a system that you can initialize and you can measure and you can control. So this could be some like cold atoms or like a quantum chip of superconducting qubits or something like that. And then you can use essentially this representation of the state, and then you can use unsupervised learning on top to like extract these features, okay? And so like the starting point, I guess is like generative modeling and more importantly like the question of generalization. And we have seen this the first day briefly. And so recall. So imagine to have an unknown distribution, and we're gonna call this Q. Q of X, okay? And X here again is a set of binary variable, X1 to Xn. But this could be like multinomial, but let's consider like binary variable. And what we have a data set, okay? We have a data set D, which is just a collection of these variables, and those are distributed according to Q. Q of X. And so the question is, can we use this data to infer the full distribution? So it's different from what was supervised learning, where you were looking at a conditional relation between images or like this set of variables and some label that lives in a smaller dimensional space. Here we're targeting the full exponentially large phase space of these variables by targeting the distribution Q. Okay, so we have all this data, and we know this is distributed according to this distribution. So like the simplest thing that we can do is use this frequency distribution, which is just essentially inverting the counts in your data set. So we've seen this on Monday too. Let's call this is frequency distribution of X, and this is just 1 divided by this is the size of the data set. Okay, so this essentially tells you what's the probability of observing one specific X given the data set. So, and this is just equal to so the probability of observing X is just the number of time that the X state appears in the data set divided by the size. Right, and this you can always do, right? You have some data and then you just count how many times you've seen a specific sample, and you just invert this and build a histogram. So essentially what you're doing is, let's do like an example. Say that you have 3 variables, so you're gonna have 8 possible states. You say it's X, and your unknown distribution is gonna have some shape. Let's call this X with the axis. Sorry, maybe it's a poor choice. And then you're gonna look at your data and you're gonna build this distribution, and you're gonna have an histogram essentially, and which is gonna be maybe something like this. Okay? And so what you know for sure is that as you increase your number of samples in your data set, the frequency distribution of X is gonna converge towards the unknown distribution. So as this increase, your histogram will converge toward the correct values. Now there is a problem. The problem is that, if you remember, the number of possible states for these n bit strings of binary variables is exponential, right? So the number of states is 2 to the n. And to have like a faithful reconstruction using this like kind of brute force inversion, you need that the size of the data set should be larger than the number of states. Say if you have like larger entropy in your data set. And so you can see that this is not possible for any practical scenario, right? So you can imagine like now building an histogram for some realistic size, maybe 50, maybe 100, and you soon realize that you're gonna have some statistics, but most of the states will have like zero counts, just because you can explore them, right? Like 2 to the 50 is something like I don't know, like 10 to the more than all the particle in the universe or something, and you're gonna have some finite size data sets, like 100,000, 100 million samples. This is gonna be very, very small compared to your phase space. So for most cases here, the frequency distribution of X will be 0. And so this what means like lacking generalization. So the problem with this reconstruction is that you can only capture the statistics that you have, and you cannot generalize past the data set. You cannot infer what's in the blank space. And so the goal of generative modeling and supervised learning is to essentially to define a model that you're gonna feed the statistic that you have in the data set, and the model will give you some interpolation, will give you an estimate of essentially the missing points. So. And so this is what we call generative modeling. And so what it means is essentially you build the models that is able to generate new samples, and also for the states that were not present in the data set. So how generative model works is that we want a parametric, we define a parametric representation of the distribution. So this called this P lambda of X, and this lambda are the parameters. I think that were called theta in Juan's lecture. And so the goal essentially is to find some set lambda star, some set of parameters in such a way that your parametric distribution P of lambda star mimics the unknown distribution X, Q of X. And you want to do this starting from the data that you have available, essentially. And so clearly there is freedom. You're going to choose this parametric distributed representation, and like the restricted Boltzmann machine is one example, but there are many different ones. And again, as somebody pointed out, this is essentially what Juan was referring to maximum likelihood. So we're going to define a cost function, and the cost function is exactly the KL divergence. So we have our model distribution, and we have some target distribution, and we want to change this parameter in our representation so that our model becomes as close as possible to the unknown distribution that is, in this case, is like represented by the data. So we want to minimize a cost function, as usual in machine learning. And this cost function has to essentially capture the distance between these two distributions. So I'm going to call the cost function C of lambda. And this is defined as the KL divergence between the model distribution P of lambda and the data, so the unknown distribution for now. And so this is defined as the sum over all possible states, and this is the average with respect to the unknown distribution of the log of Q of X divided by P lambda of X. And so when you break the logarithm into two, get sum over X of Q of X log of P lambda of X, and then you get this other term which doesn't depend on the model, right? This is just the entropy of the data of the unknown distribution, right? So we don't know this Q of x. That's what we are trying to learn, right? But what we know is that we have the data set. So we can approximate essentially this expression with our frequency distribution. That's what we have in our data set. So, sorry, this is sign. And so, so we have the average over the data. So we are essentially approximating this Q with the data set. So xk in the data of the log of p lambda of xk. And then here we have minus the entropy of the data, which is minus this term. Okay, this is a constant term, doesn't depend on the parameter. So when we're gonna minimize this cost function, which means we're gonna take the gradient of this with respect to lambda, this is just gonna cancel out. So I'm not gonna like dragging this around anymore. It says maximum likely we're gonna find, we're gonna essentially seek this optimal value of these parameters, and this is done again by one of the flavor of gradient descent. So like the simplest one, you just take your lambda and then you modify it according to the gradient you expect of the cost function. So this is the learning rate, is your step size, same thing as yesterday, and so gradient descent. And there are many different types of gradient descent. This is like the simplest one, but I mean this is the general philosophy. Okay, good. So now what's left to decide is what's p lambda. Okay. And so as p lambda, we're gonna define now the Boltzmann machine. Okay, what it is? Boltzmann machine is importantly is an energy-based model. On a graph. Okay, what are the features? So again, you have nodes, or like neurons, which represent your variable xj, and then you have the edges with some weight wij, and these are essentially the conditional dependence between your variable. And so what it looks like is just a collection of units fully connected by these edges. So this is xi, this is xj, this is wij. Okay. So one difference with the feed-forward neural network is that in the feed-forward you have a clear direction in your conditional dependence. So you start at an input layer, and the signal propagates through in a well-defined direction. Here, the graph is undirected. There are no edges, or if you want, there are bidirectional edges. And the other thing they want to look is this variable xi, xj. They can either be 1 or 0, while yesterday they just be equal to the sigmoid value, so they could have any value between 0 and 1. And so it's an energy-based model in the sense that given this graph structure and these variables and these weights, you can define an energy. E lambda, I'm gonna say what's lambda now, of x is minus sum over I and j, b ij xi xj. And so the parameters essentially here are just the weights. So does anybody recognize this? Exactly, yeah. It's a Ising model. And the only difference is that what we see in the first day was built on a square lattice, and this interaction were between nearest neighbor. And here, this built on the fully connected graph, and everything interacts with everything else. And also the variables there were plus and minus 1. Here we have zeros and 1, but it's just a matter of rescaling the whole energy. There could be also some additional terms here, like magnetic field. I'm just not going to use them for now. Just introduce them later. So this is not yet a restrictor. This is like a general Boltzmann machine. And the other important property, now this model is not yet probabilistic. It's just an energy function. That's actually called the Hopfield model. It was proposed before the Boltzmann machine, just like a deterministic model. But what we can do is that we can essentially place the system at thermal equilibrium. So we can insert a temperature. So beta, or like inverse temperature. And this gives a probability distribution P lambda of x, which is 1 over z lambda e to the minus beta e lambda of x. Right? Same thing as the Ising model. So our z, the partition function, is the sum over x e to the minus beta e lambda of x. And so that's why it takes the name of like Boltzmann machine, just like a neural network described by like a Boltzmann distribution. So now we have a clear representation of our probability, right? The parameters that we want to tune are essentially the interaction. So you can imagine this as a neural network with some weights, or you can think of this as just like an Ising model interacting, and the unsupervised learning part that we're gonna see in a minute essentially correspond to find like an optimal set of interaction between this neuron, right? Sorry?
The W needs to be positive or the negative?
Yeah, the question is if the W needs to be positive. No, they can be positive, negative, anything, essentially. Yeah. So it's not like a ferromagnetic model, right? It could be anything. Okay. Okay, so let's see how to discover these weights. Okay. And I'm gonna do this small derivation for the Boltzmann machine. It's gonna be equivalent for the restricted Boltzmann machine, but it's a bit more intuitive for the Boltzmann machine for this type of network to understand exactly what the learning does. And then I'm just gonna rewrite it for the other network. Okay, so remember, this is the thing we want to minimize. Okay, that's a log of the probability distribution P of lambda for data points, for configuration that appears in the data set. And the way that we change the parameters is according to the negative gradient. So I'm asking, okay, what's the change in the interaction that we have to do to increase the likelihood or decrease the negative likelihood of the model? And so this is proportional, that is the learning rate, but well, to minus this is the derivative with respect to wij of the cost function, okay, which is just the average of the log probability of x with respect to the data. That's what I'm calling here. And there is a plus sign there. Yeah. So I have minus the gradient of the cost function, but the cost function has a minus already, so I get a plus here, right? Okay. Now, this is just an average over a data sample, so let me just take the derivative for 1. So the derivative with respect to wij of log P lambda of x. Okay, so we can just write this. We know what P lambda is right now. And so log P, we get a minus beta E. And then we have the minus log of Z. Right? Just plugged in P lambda and took the logarithm. And so when I know what A is too here, so I'm taking the derivative with respect to the interactions. So what I just get essentially is, I'll just take the beta in front here, and I get the xi times xj. I get the correlation for that particular bond that I'm taking the derivative against, xi and xj. And then, well, I get the derivative of log z, so I get minus 1 over z, and z, I know what it is, I just plug this, and it's the derivative, and then I get e to the minus beta e of x. Okay? Just like the, and so I know what that derivative is too. Essentially, it's just so e divided by z is just the probability. So I get p lambda of x, and again I take the derivative, I get two minus signs, and I get the derivative of e again. So it's the same correlation, xi, xj, right? So now this is the derivative of the log probability for just one samples, but my learning signal, I have to take the average of this with respect to the data. Now this does not depend on that because it's the average already with respect to the model distribution. So my final changing weight is beta is the average of this with respect to the data, xi, xj data, minus xi, xj p lambda. So you see that this difference between essentially the average correlation function from the data set minus the one calculated with respect to the model. Okay? And this is very important, it's going to be the same essentially for the restrictor Boltzmann machine, but we're going to have latent variables, and so.
The sum over there was over the data set, right? There is an approximation. The underlying sum is not over all states, but only those with over the data set. Yeah.
So the question is, if the sum is over just the samples in the data set, yes. The approximation was done before here. So here I had the sum over all states, and approximating this from the data set.
Probably in the last step, when you say xi, xj over lambda, this is over the very last term. That one is not the expected value under p lambda.
Yeah.
It's approximation.
No. There is no approximation here. This is the average value of this correlation function on p, and I keep it like p as the full, like this is an equal sign between these two. So this is just, it has still a full exponential sums in it. We're gonna deal with this later using Monte Carlo, but so this is
yeah.
So the point is, this is easy to compute. This is hard because this term here contains the partition function. The sums runs over 2 to the n, and we're gonna, and those actually have two different names. It's called the positive and negative phase of the learning, and the positive phase is trivial. You just do that sum on the data point that you have, and you can do it like in the size of the data set, which is not exponential, but the other is not. Okay. And so what they are? Let's see what does it mean. Positive phase. That's the xi, xj over the data. Okay, so let's see. So the change in weights. Let's just look at this piece here. Okay. So if the 2-point correlation between this variable is positive, okay, let's assume that in the data you have this positive correlation. So what this term wants to do is to increase the interaction between these two variables. Okay. And so we look here, if we increase the interaction and these are positive, we are effectively decreasing, we are trying to decreasing the energy for states that contains this type of feature, this type of correlation. And decreasing the energy means that we increase the probability. So the positive phase, what it does, it says, look, I want to essentially change my energy and my probability so that the data point that are in the data set becomes more and more probable. Okay? So you want to do this with this positive sign. And the other term does exactly the same thing with the reverse sign when you average over the model. And so essentially what he's saying is try to remove all the spurious features that are introduced by some incorrect knowledge from your model. And you can see that then when these two terms, they are exactly the same, then you don't get any change in the gradients. So essentially the correlation that your model generates matches the one in the data, so you win. And the point is that the positive phase is negative phase is easy to compute, while the negative phase is driven by P and still and exponential sums that we're gonna deal with Monte Carlo. Is there any question about this? Is more or less clear? This kind of philosophy, right? You remember again, we want to find a set of parameters lambda so that this P of lambda matches our data. So we want to increase. If we look at the x that is very probable in the data set, we want P lambda of x to be very high, or as high as is in the data. Okay? Okay, well, so this is pretty much like a full prescription how to train this model. We have a learning rule, we have the parametric dependence, and so you can ask yourself, I can just try this with any data set and this should work or not. So the first question is, can I optimize this model correctly? Can I actually solve this optimization? And that clearly depends. And the other more important question is this P of lambda powerful enough? So can this P of lambda actually capture like a wide range of unknown distribution? Is the representational power what we call, what is it large or not? And it turns out it's not. It's very little actually. And one of the problem of this model is that it can only capture pairwise correlation. So there is a little exercise that you could try, and you could try to see if you can learn the XOR function with this. You could and you can actually show it by hand. And the XOR is just, you have three variables, x1, x2, and x3, and it just takes the XOR operation between these first two. So 0, 0, 0 is 0, 0, 1, 0 is 1, 1, 0 is 1, 1, 1 is 0. Okay, and so what you're asking is that, can I build a Boltzmann machine that generate this distribution so that if I give these two values, the third variable will likely select this one here. And it's impossible. It's like a very simple function. It can be learned by RBM because it's a parity and it's a third order correlation, and the Boltzmann machine cannot. And so this is one reason that this is a very, very nice and instructive model, but it's not very powerful. And there is a simple way to make this the Boltzmann machine powerful, is that you're gonna add hidden neurons or latent neurons, right? So what you're gonna do is you take your x and you essentially change it to a visible variables. Those are the variables you're trying to describe, you're trying to learn, but you're gonna add more. You're gonna add some hidden neurons. So essentially now your network becomes something like this. You have two different types of variables. You have visible variables and hidden. So in the example before, if now you're trying to learn the XOR function, you have three visible variables, and you add even only one hidden, then this hidden allows you to capture this high order correlation, in this case like third order. Okay, So the data distribution before was Q of X, and now it just becomes Q of V. So the data does not have anything to do with your hidden variables. That's just what you're gonna add in your model to essentially to allow you to capture this larger class of distributions. And so we're gonna have also a new energy function, right? So it's still like a Ising model, just it couples all these variables with some interactions. But now our P of X of the model also becomes a P of V and H, right? So this is the joint distribution that we were looking yesterday. But recall that in our cost function, this is minus the average of our log probability. So we have the log of our model, but now this probability is defined only on the visible layer, right? So we want to make this probability close to the data. But what this means that, and then we have the cross entropy. What it means that we need to access this marginal, right? And so what this P lambda of V, this is just the sum over H of P, V, and H, okay? And so we need to obtain this probability to use it for the training, for the learning, and the simplest way to essentially to do this sum and obtain like a tractable marginal is to restrict the interaction. That's why it's called restricted Boltzmann machine. So we split the visible and hidden variables into two layers, and we consider only interaction between the two different variables. So we have eliminated all the interaction between variables of the same type. So these are Vij, this is Hi, and this is Vj. And so our energy is a function of V and H. You have the sum of the interaction between the hidden and the visible, right? No intra-layer interaction, and then we can add also some magnetic or some bias, which in the Ising language is equivalent to magnetic fields. And so this is the energy function that you're gonna find for the standard restricted Boltzmann machine. This is Bm. And again, our restricted Boltzmann machine probability is just going to be the Boltzmann distribution. And so I'm going to set the temperature equal to 1. It's a choice. It's a standard choice, but you can feel free to change it. The higher the temperature, you're flattening essentially the free energy. But this is like a standard choice, and it works fairly well. Okay, so if you compare with the previous one, essentially the only thing that changed, you still have a Boltzmann distribution. And now you have an additional set of variables, and you're looking at the interaction between these two layers only. So no intra-layer interaction. And it's going to be clear in like a minute why we do that. Okay. Okay, so our cost function contains this marginal over the visible layer, and we want to minimize this, so we won't need to take the gradients as we did before. And to take the gradients, essentially we need to compute this first. We need to take this sum explicitly, so that's what we're going to do now. So P of V, this is the sum over H of P lambda and V and H. Okay? And so let's have 1 over Z. So I can, this part here does not depend on H, so I'm just gonna put it in front. Just me say transpose V, just shorthand notation, okay? And then we have the sum over all possible hidden states. So let's say we have m hidden variables. So this goes 0, 1 for all of them. We are taking the trace, okay? And then we have the energy. So these two terms here. I'm just gonna take the HI as a common factor. HI, okay? So because of this, because we can factorize this term, then we can do this sum exactly. So this is essentially equivalent B transpose V. Now we have the product of all the hidden units of the sum of HI 0 and 1 of this E sum over J I of HI. And the reason is because the hidden layer, they are not talking to each other. If we had some interaction between the hidden layer, then we could not have done that. Okay, so we can do this. So 1 over Z B transpose V, and then this is just going to be the product over I, and we have, so when H is 0, this is 1, plus when H is 1, this is E to the sum over J via J Vj plus Ci. Okay, and so for sure we can essentially define a new like energy which is called like epsilon of X, and this X, sorry, of V. Did I say X anywhere? No. So let me just write this because it's going to be useful for later. Log. Okay, so I just rewrote this as an exponential, so I just took a log here. And so the point is that essentially after integrating, after doing this trace, what you're left out is, again, it's a Boltzmann distribution, okay? So you started with the Boltzmann distribution in V and H, and you did this trace, and because there are no connection here, so you can factorize your hidden contribution, then you can do this sum, and what you end up is a new Ising model, if you want. But as you look at the energy of this Ising model, you see that it still has this term, which is kind of like a mean field, magnetic field for this variable V, and then at this log, okay? And this is the nonlinearity. This is how your model becomes expressive. If you take a Taylor expansion of this in V, essentially you're going to have correlation between Vi and Vj at any order. So you don't have this problem anymore. Now you can essentially capture any correlation with this energy function. And so let me just like summarize a couple of points here. So this energy contains the correlation between V at any order. Okay? which is very, very welcome. The other point here is that I haven't said that, the number, as yesterday in the supervised learning, the number of hidden units is one of these hyperparameters. So we can increase this number at essentially as we want. And so this is a, direct control on the representational power. So we can define a number, which is the ratio of hidden and visible units, and as we increase this, essentially, we can capture a larger and larger class of distribution, which brings to the last, and that RBMs are universal approximators. Of discrete distributions. And so what this means is that this is proof, there is a theorem, and provided that you have enough number of hidden units, you can essentially discover a RBM which like mimics mimics an unknown distribution to arbitrary accuracy. Okay, always there is a catch, of course, that this number of hidden units might be exponential. And so the worst case scenario, if you have n visible layer, n of these neurons, and you have 2 to the n hidden units, and you are sure that you can find a representation of any distribution. But of course, that would be like very, very inefficient. So the question is, can we find some efficient representation with a number of hidden units which is small, maybe order n, or something like that, so alpha equal to 1 or 2. Right. And so what we're gonna, so this is essentially the representational part of the network. So we define our parametric distribution. And so tomorrow, the first hour, we're gonna see how in practice we can find this set of parameters to mimic an unknown distribution. So there are some tricks, especially to evaluate this negative phase, which has this intractable sum. And so we're going to use Monte Carlo, similar to what we see in the first day. More precisely, we're going to use Gibbs sampling, a special case of Gibbs sampling. And so the tutorial essentially will be just using this model to learn the Ising model that you generate in the first day. So we're going to train a restricted Boltzmann machine so that after the training, it becomes indistinguishable, if you want, to a classical Ising model, training on that data. And then the other hour, we're going to look at some application, like quantum many-body physics, and precisely how to use this to reconstruct quantum states, and also gives you some mean to augment quantum experiments and stuff like that. Yeah. Any question? Yeah?
So this thing is arbitrarily often differentiable, I take it.
This thing is?
Not smooth, there are no kinks or anything.
Yeah, no, the question is, this is arbitrarily differentiable, there are no kinks, and yeah, this is a smooth function, and you can, yeah, exactly.
No convexity.
There is not. So, I asked if no convexity, so in the original Boltzmann machine with no hidden neuron, the training can be convex. But as soon as you add hidden neurons, that you lose this property of convexity. So your landscape of your optimization is going to be all bumpy, and so this is one of the challenge in actually training this. But there are many techniques to overcome this problem. Yeah.
You talk about the linearization of the energy function with respect that depends on the visible data, right? You talk about the linearization of this.
Linearization?
Yeah, linearization. Well, taking the first order Taylor expansion.
Mm-hmm.
That's linearization.
Yeah.
Okay. based on the use of the rectifier linear units, that they say that is the best activation function. Do you believe that if it's useful that instead of doing a Taylor expansion, we can use rectifier linear units in order to approximate each exponential that is described in this function?
Okay, so the question is, since we can take the Taylor expansion of this, since the rectifier linear units, they're like very powerful activation, why can we use that instead?
In order to approximate.
Yeah, so that's true. I mean, those are very, very powerful for that, but we're never gonna take the Taylor expansion of this. What I meant is that, this term is what gives the model its power, meaning that it can capture this higher order correlation. But in practice, we will never do any Taylor expansion. We will just consider this and take the derivative of that, and this just gonna give you the learning signal. And we're gonna have an activation function for our, I haven't explained that yet, I'm gonna talk about that tomorrow when we sample them. We have an activation function, but that just naturally comes out the probability distribution. So you can't really change it to ReLU without disrupting the whole model. But I guess this is gonna come clear tomorrow when I tell you exactly how do you sample each neuron, how do you assign a value to its state.